All right. Okay, so hello. Today we are presenting our presentation on different structural elements for the fuselage, truss, monoc and semi-monoc wing constructions. So we start off with a truss. We gathered like a few examples, some very recent, some very early. So the first example that we have for you is the Boeing transonic truss-braced wings. The wings for this aircraft, it definitely it has a higher aspect ratio. The reason why it was able to achieve that was because of the wing brace structure in the front of like the aircraft. The higher aspect ratio means that this aircraft would produce less induced drag and thus is a more efficient design.
So I did the Wright brothers, the first airplane, and you can't really see here, but in between the supports there's wires that act in a V, and those form a truss structures in between the two wings. The overall wing is made of fabric, but the struts are wired. And to find the aspect ratio of a biplane, I originally thought you just multiply the aspect ratio by 2 because it's 2 sets of wings. But it was sort of like a roundabout explanation that you need an aspect ratio for each wing that's double of its mono wing equivalent. So yeah, you can see here that it's the first one, so you can't really hold them to that, but that is has a lower aspect ratio, but it was enough to get them a couple seconds in the air, so it ended up having a lot of drag, but yeah.
So this is the Harel Dubois HD34, and this plane was mostly used for aerial photography and surveying land. And it was specifically surveying land in, parts of France and remote parts of Africa. So they needed the wings to be reliable. And part of the benefit of the truss wing design is that there's usually a redundancy in the load-bearing structure. So if part of the wing breaks, it's easy to repair, and usually it can keep flying. And it was also built for long distance and low speed flights. So it didn't need to have like high maneuverability or high speeds.
So I looked at the Boeing Stearman Model 75. So this was the prototypical plane that the American military used, mostly during World War II. And it's similar to the Wright brothers aircraft in that it's like a biplane structure, and it has beams that sort of connect those two wings. And it was because of the truss structure, it was capable of low altitude and low speed flight. And similar to like what was earlier discussed, it could be used for surveying as well, but it was used as well for crop dusting and seeding tasks because of the low altitude and low speed.
So this is the de Havilland DH-88 Comet. And so this plane was built to be fast. It was actually built specifically for a race. And so they went with the monocoque design because the wings were made out of laminated wood, which is a very lightweight material. And so because of that, it was able to fly very fast, and it was like very lightweight and efficient. And yeah, so they used laminated wood to form strong and lightweight wings.
So a monocoque design is the Boeing 787 Dreamliner. This fuselage is made of 80% reinforced polymer composite, and the wings slightly curve upwards to account for the extreme forces that it feels during takeoff and landing. Mostly, it's curved upwards to deal with the forces from landing because you're working in the same direction as gravity. And yeah, the plane is a very heavy plane, so it needed to have a higher performance, and able to have this curved wing design allows it for it to work with the aerodynamics and not fight against it.
Those things are true, but it's not a monocoque construction.
No, I looked it up. It said it was on the Boeing website.
Any particular part is in this monocoque?
It's at the wings.
Wings are monocoque?
Yeah. I can double check, but
Sure, sure. Because for its high level of performance, it's kind of very difficult to have it monocoque.
Yeah,
I would
that's so.
presume it is semi-monocoque.
I thought so too, but I found a couple of resources that
Okay. Okay. Yeah, I'd be happy to hear next class, maybe clarification of that.
So I looked at the Hawker Hurricane. It was a British fighter aircraft used during World War II, and it used fabric as the outer skin, and it had very little bracing inside, and it was pretty lightweight because of this, and it was meant to be fast because obviously it's fighter aircraft. So yeah.
So this last plane here is also a racing plane. It's like a high-braced, high-wing monoplane, and it was built for a specific race. It was the first plane to break the 200 kilometer per hour speed at that time, which was in 1913. And the use of the monocoque design and the material chosen, which was mostly wood, that was used to create a lightweight but strong fuselage.
So this is the Mitsubishi A6M0, or also nicknamed the Zeke. And so this was a Japanese World War II plane. And this plane was designed to be fast and have high maneuverability. So a monocoque design wouldn't work here. They made a semi-monocoque design for the wings that were able to withstand the loads during those high maneuvers or aerial attacks. And it was also built to be strong and while still being not super heavy weight-wise.
So I looked at the British ARV Super 2, also called the Opus, and the whole plane is made up of a couple different composites. The fuselage is an aluminum alloy. It's used with Superall, which is a super plastic adhesive, and the wingtips are fiberglass. So this plane was designed to be a trainer plane and a cheaper alternative to the current, at the time, Cessna 152, which was the standard. And yeah, so this plane has a semi-monocoque design, not only because it wants to perform well, but also because it was meant to be cheap. And having it being able to withstand stronger forces with less material means that production cost would go down. So the wings have a slight 5-degree sweep, and it has a relatively small wing area with only 92 square feet. Again, this is for the cost, and it was only a 2-person trainer aircraft, so it didn't need to be huge. And it had a wing loading force of about 11.9 pounds per feet.
So I looked at the Lockheed Martin F-35. This is a stealth fighter aircraft, and so to account for the high loads and also to be light, it used it had a thin skin, but to account for the high loads, it had internal frames and stringers, and so yeah, to handle and distribute the load that would be experienced during the missions.
Okay, and for my aircraft, this is the ATR-72 anti-submarine warfare aircraft. This is also a military aircraft, and it was used for anti-submarine and anti-surface warfare missions. This airplane has a semi-monocoque design with a fail-safe fuselage, mainly because it's going to be in combat, right? It needs to make sure that it is reinforced, and it's made out of composite materials, making it both lightweight and strong.
So I looked at a different research study. It was looking at the properties of wing angle, but in their control testing, they did have some data on skin cover thickness versus wingspan. So you can see here, they didn't specify which plane they use. I don't know if it was a military aircraft and they couldn't specify, but they said it was about a 200-person capacity. So you can see here it's broken up into the skin thickness of each element of the wing. So you can see that the upper skin is significantly thicker than the lower skin, and then it also calculated the torsion, shear, and stiffness based on this. And here was another rendering that they did regarding the failure index of the upper and internal and the bottom skin layers. So you can see that the failure index shows where it is experiencing the most stress in certain scenarios. So you can see consistently for any of the skin layers, it's right about where it is adhered to the aircraft. So this could be due to the adhesive used or just due to the sharp angle. But yeah, here you can see that overall, this specific plane that they looked at was pretty good at redistributing the weight, except around that part where it connects to the fuselage.
Just a clarification of this. This is for probably the same aircraft that they have done for different kinds of designs, or is it as you move along the span of a single design, you're looking at the skin thickness coming down? I think it's probably the latter. Right?
Yeah, I should have specified. It is, the skin thickness does vary in this aircraft that they looked at. So this is saying that in this specific aircraft, because they only studied one, as you go further out from the base, the skin thickness gets a little thinner because it doesn't need to withstand such stronger forces.
So that's something which would be, though it might be plotted, the actual numbers might be for a specific aircraft. This is something that is commonly observed for all aircraft. So I think this is an important thing to observe, that as you go outboard, because usually the lift distribution will be nearly elliptical, so you'll have hardly any lift at the tip and a very large amount of lift at the root. So the bending moments will become very large as you go close to the root. So you need much larger thickness in order to withstand that. And it's actually a very informative plot because they've separated out your torsion and the bending moments and what is taken by different parts like the upper skin, lower skin. So I'm glad you laid your hands on this.
And then this was another graph that I found on the left. I couldn't find an exact one like I could before where it directly correlated between skin thickness and the gross weight. But here it was just an informative graph to show the distribution in an F-16 of the different types of composites.
I ended up finding like this this graph specifically for a different comparing different helicopters and their surface area compared to their fuselage weight, and we can see as the body surface area increases, the fuselage mass would also increase. This isn't specifically related to airplanes; it's related to helicopters. But yeah, I thought it was informative. So yeah.
Okay. I'm not sure if I came across clearly in terms of what I wanted for the homework, because I really appreciate that you have collected information about specific aircraft of different types, and it's nice to see that in each type some of you had fairly modern aircraft and some of you had even fairly old aircraft, starting all the way from the Wright brothers. So it's quite clear that none of these design philosophies are outdated. So whether it is the truss or the semi-monocoque or the monocoque, they all still work. It's just to find the right candidate application. Is the aircraft small enough or slow enough in order to have a non-semi-monocoque construction? Because most aircraft today, modern aircraft, are made semi-monocoque, which is why I was kind of surprised when you said 787 is semi-monocoque. So I mean monocoque, because I thought it is semi-monocoque. You can just bring that particular source in the next class, and we can project it and try to read it up and have a small discussion on that. But otherwise, what I really wanted was, and maybe you could try it out in the next class, is to find the actual skin thickness for a specific aircraft, and try to do that for as many aircraft as you can. And you come up not with a plot from the internet source, but you sketch a plot in which you plot the for different aircraft. So one point will be there. For each aircraft there will be a point which refers to its skin thickness and its weight, its skin thickness and its wingspan, so that then we can see as many aircraft as you can probably lay your hands on. As one of you pointed out, it's true that I think Alexandra, you pointed out that the skin thickness varies along the span. It's true. In such a case, if you have data for the entire thing, you take the average. So whatever is the average thickness, because all that I am interested in is, given a span, what is the skin thickness, and when there's a different aircraft with a different wingspan, say larger, obviously you're going to have a different skin thickness required there. So then what happens is that you're essentially, it's almost like some of you presented pictures from Raymer, for example, which is the very good aircraft design book. What really helps you there is that you do a case study of multiple aircraft of different classes, and then you see is there some kind of a clustering happening of points, because each point represents an aircraft. So the skin thickness can be a function of many different things, but we are looking at it purely from the point of view of the wing span, of the gross takeoff weight of the aircraft. Maybe you can add another thing, which is the cruise speed of the aircraft. So we could have 3 plots like that. Then we see from the clusters, we'll see probably that when the wingspan increases, it means that we are having larger aircraft, which means that you probably have larger loads, which means that you'll probably have larger skin thickness that is required. So I just want to see some kind of a correlation there. It may not, because this data may not be so widely available. You might have to do a little more deep search in order to try to try all kinds of sources. And I think I mentioned Flight International and some magazines like that in the last class. So you just try to see if you can find some data from those, and so that we can then discuss over those plots. So because one of the things, takeaways from the last class, sorry you were not there, but hopefully you got to see the video or something like that. So the main takeaway from that was that why shells and beams. And the main thing that we were trying to look at is it's okay to have shells as far as smaller aircraft are concerned, slow speed aircraft are concerned, but once you want to increase the performance, the loads become large. You can't have just the monocoque alone, which means not the shell alone. You need to have stiffeners, a skeletal structure to go with that. And that was the whole idea. So it may so happen that once this kind of correlation is not as anticipated, for example, I'm plotting the skin thickness versus weight, let's say, I would expect it to kind of increase, monotonically increase. But it may not happen because people might have shifted from monocoque construction to a semi-monocoque construction, so that the skin thickness would have dropped what is required, because now these are these spars and stringers, they are taking the load, sharing the load rather with the skin, so you don't need that much of a skin thickness. So that's essentially the takeaway I would like to have from your plots. You had something to say? Yeah.
So like for whatchamacallits, the for like the plots, if we were to show them for next class, would you want them like separated into like 3 different lines for like truss structures, like the semi-monocoque structures, monocoque structure? Just
populate them all on the same plot, like
okay.
For example, if I just want to plot the skin thickness here, we call it average skin thickness because it changes. So typically for the wing. And then I plot it versus maximum takeoff weight. Okay. So you can actually mark the units, whatever, and data, and then you'll see one particular aircraft you might find it here, another aircraft you might find it here, some aircraft you might find it here, like this. Some clustering might happen. So this could be about a dozen different aircraft. For each aircraft you have a point.
Okay.
So then we can start discussing what does this cluster mean, what does this cluster mean, what does this cluster mean. Then you can probably have different symbols. Let's say some of these could be so triangles or squares, or let's say a star. And then you can have a legend which says that this means truss-like aircraft. This is semi-monocoque, and this could be monocoque. I'm just saying these could get interchanged, and I'm just trying to explain what I'm trying to look for. So that then we can discuss based on the kind, and it's also possible that there might be a square in this or some triangle in this. It's not that all of them might fall in the same thing, but then those are the outliers. Then we can discuss what could be the reason for those outliers. Why is one of these triangles occurring along with a star, or why is another square or rectangle occurring with a star? So it may not be hard and fast that they fall into clusters like this, and some of them might not be so closely clustered, they might be spread out, whatever, because this is not some kind of analytical function that you're trying to plot. It's just arbitrary data from different, and there could be all kinds of aircraft. Some of them could be fighters, some passenger aircraft, some trainer, acrobatic aircraft, etc. So based on that also there can be a shift, but at least to give us some ideas into what is the main dependence of the skin thickness, which is a structural decision we make as structural analysts and or designers, and as a function of the size of the aircraft. So that's essentially what we are trying to look at over here. And similarly, instead of this, you could have the weak grooves. So another plot for that. And similarly for, let's say, the span, okay? The span of the wing. So that way we get an idea of what is, and these may not be the only things that are dictating the skin thickness. There could be so many other things. It all depends on the load. It also depends on the different materials they use. Some might be using better materials, so they might be able to come up with lower skin thickness. So we're not comparing actually apples with apples here. There are lots of apples, oranges, and maybe even vegetables over there that we're trying to compare. So, but all said and done, as a team, we can then sit and think why such clustering is happening or not happening, and why some outliers are there. So let's reason out. So it's a very educative exercise where you try to understand from an overall perspective of the geometry selection, because there's one thing which is material selection, which we'll go through in today's and probably next class. We'll be focusing more on that in the class itself. But this is something, if not as important, sometimes even more important than the material choice, because many cases material choice is almost a given, depending upon the best material you have at hand and which is available or which is economical for that application. So you don't probably have too much of a variation. But these geometric features, you have a lot more play around. Overall shape, you don't have a play around, because the aerodynamicist will tell you this is the airfoil I want. So you don't have and this is the chord I want, this is the span I want. Within that you can play around the skin thickness, the spar, how many spars to have, what is the area of cross section of each spar, what is the area of the flange, what is the area of the web spars cross section. All these things we just play around with. So I think that's the whole idea. It can give us a lot of useful takeaways. Thanks. Okay, so in the previous class we were focusing on some of the components like the wing skin thickness. Other than that, we were looking at the spars and stringers. One of the things that typically gets overlooked at are these transverse members. The transverse members we discussed in the fuselage were these frames, bulkheads, etc. And in the case of the wing or the horizontal and vertical stabilizers, these are the ribs. So we will just take a look at some of the examples from what is available in the open public literatures, many of them from Flight International and such other magazines, and some from company websites as well. Yeah. Yeah. So here you see, for example, a horizontal tail, and you see the cutout, which means that the skin is taken out, and then you see the skeletal structure which goes in. If this skeletal structure were not to be present, you would have needed much thicker skin, and the overall weight of the horizontal tail would have been much more than what the overall weight of the structure here is. So which is why this semi-monocoque construction is important in this particular example. And here you see these structures, which is our focus on right now. So this is along the span of the horizontal tail, and along the span of the horizontal tail you see that there are longitudinal stiffeners, which means along the span, and those which are perpendicular to the span or along the chord, which is what we call as these transverse stiffeners or ribs. And typically you would see, whether it is in the tail like this or on a wing, you would see that there are cutouts. These are holes at the center that you see on each one of these stiffeners, and these are typically there. One is because anyway the center portions will not be taking much loads, so you would not require material there. The other important practical reason is that this could double up as let's say a storage space for something, or it could also it will also include control lines going to the elevators, because this is the horizontal tail, remember, so it will be connected to the elevators. So what is shown on the overall aircraft over there, it is the portion A that we are seeing, the blown up pictures over here. And there you would see that you might want to deflect the elevators in order to change the pitch angle of the aircraft, and therefore the angle of attack, and therefore the speed, and also the altitude. Many other things can be controlled with that, which means that there need to be control surfaces which are at the end, at the trailing edge, and there are control lines which run, which could be mechanical and or fly-by-wire, which is electrical, etc. So but you need a pathway for them to go, so therefore these holes are utilized for that. In the case of a wing, for example, these could be doubling up as a fuel tank, in which case you might have bladders of fuel in each one of them connected through each other by pipes and or valves in order to make the flow happen. So if you have bladders like that, can you guess? So this is the tip and this is the root. Let's say instead of a horizontal tail, we are looking at a wing over here, and let's say it has fuel tanks, which means bladders of fuel in each one of them. How do you think the fuel will typically want to be spent out? Would you spend those which are the fuel which is closer to the tip first, or would you like to spend the fuel which is closer to the root first, or anywhere it doesn't matter? Would you have any take on that? Yeah.
Would you go closer to the tip? Because, like, I'm just trying to imagine, like, if you spend the fuel, like, closer to, like, the body of the aircraft, like, would that fuel, like, redistribute?
Yeah.
Oh, okay. So probably, does it matter?
Is there, yeah, that's what I'm asking. Is there, does it matter? Or you think there could be an advantage, disadvantage?
Yeah, probably closer to the body first, because there's already, like, so much stress that's happening near, like, like, near where, the tail and the body is going to be, like, adhered to, right? So if you got, like, if you get rid of, like, the fuel closer to the body first, like, stress, like, between that adherence between the two efforts?
Good. You're thinking on the right lines, but the answer is exactly the opposite. But but the logic is you are getting to the logic. So I want you to think a little more and see what's actually happening. So now we are no longer considering the tail, thinking of this as a wing, because rarely you will put fuel in the wing, in the tail. It will be mostly in the wing. So let's come to the wing. What is the main purpose of the wing, aerodynamically speaking? Left, yes, right. So which direction does the lift bend the aircraft in? Yeah, and what is the fuel or any weight for that matter doing? Which direction? Is it also bending, and if so, which direction?
It would be bending.
Yeah, bending in the lift. Yeah, lift is bending the wings this way, right? What is the weight of the fuel doing?
The weight of the fuel.
Yeah, right? So which is going to be larger?
So it would be larger near like the lift would be larger.
Yeah, obviously, right? Because the lift is of the order of magnitude of the weight of the whole aircraft. Whereas this is of the order of magnitude of the fuel weight, which is a very small fraction of the overall aircraft weight, right? So which means that the main load which is coming on the structural elements of the wing is trying to bend it upwards. But any weight, be it the fuel weight, be it the engine weight, be it the self weight of the wing, all of these are trying to bring it down, which means that they are actually trying to help from a structural point of view. They are actually reducing the bending moments at the root, right? So now can you probably rethink and say which fuel would I want to spend first, the one close to the tips or one close to the wing? Which bladder would I want to finish first? The one? Why?
Because if you have less weight on the outside, there's less reason for the wing to bend downwards.
Yeah, but is that bending downwards advantageous or disadvantageous?
In what context?
Because we were just discussing the main load is the lift. So it is already bending upwards quite a bit, which is what is causing the main stresses. Right? Now this, whatever is the weight, including the fuel weight, but all other weights as well, they are trying to give me some relief. They are trying to bend it in the opposite direction so that now it's not bending as much as it was earlier. It's bending much lesser, right? So now can you rethink and answer this? Yeah, which would you like to finish first and why?
So the fuel on the outside can be like a counterweight to the lifts curving upwards.
Absolutely, absolutely. So you would want to finish the fuel here first because this is going to this has a much larger momentum. Because it has a much larger momentum, because the weight is acting over here. The weight multiplied by this distance is what is the bending moment, right? So you want to keep that for longer. If it's a long haul flight, you would want to first finish off these things and then finish that, so that till that at least the stress will be much lesser than. It's not that the aircraft is not designed for the stress. If all the fuel were still there or not there, it will be able to take. But lesser the load, always the better, because it's going to have the life of the structural components elongated. So it will last for much longer before it needs to be overhauled or something like that. So wherever possible, we try to reduce the stress. And these are like some minor ways in which you can enhance the relief and therefore enable the structural analysis. So a lot of these things are very interesting. So this is just a sample example that I'm giving, where a non-structural decision can actually have structural implication, in the sense that where you put the fuel and which fuel you burn is more of a propulsion engineer's decision or whatever, but it has a huge implication for the structural engineer, because you see that the structure can last much longer. So that is the whole idea of trying to look at other opportunities, non-structural opportunities, in order to reduce the stress levels. Yeah, and then this picture you look at, one example is of a lifting surface, the other is of a containing surface, which is of the fuselage. And here also you see, in addition to longitudinal members, here they get reversed. Here it's along the span, which is longitudinal. Here it is along the length of the fuselage, which is what is the longitudinal stiffening members. So they are usually almost perpendicular to each other, the way the wing is placed perpendicular to the fuselage length. But the functionality remains the same. So the stringers will take mainly the axial and bending loads, both compression and torsion. So here, of course, there's not much of aerodynamic force, but mostly it is the self weight and also the weight, the loads coming from the wing, the loads coming from the tail. If the engines are attached directly to the fuselage, as it is in many aircraft, then the loads coming from the engine, both the weight of the engine as well as the thrust of the engine, all of those are going to cause loads. And to take care of that, you have the skin protective as well as taking part of the load, and then the stringers taking mainly the bending load. But our focus here is on the less noticed transverse members, which are also equally important. And these are what you see over here, the frame-like structures, which are located at certain distances from each other. And when you have a cargo bay, or let us say doorway for the passengers, etc., you have much larger cutout in them. But you would see the cross-sectional area closer to such large cutouts is much larger compared to the other frames. So some of them might be just what we call as formers, FORMERS. The idea is to keep the form as it is. In other words, you want to retain the shape and size of the fuselage. The skin should not have too much of a deflection. So all that their purpose is to maintain that geometry, which means that they may not be having very large cross-sectional areas, because otherwise it will be too much of a weight penalty, it will be a overkill. But when it gets closer to these kinds of cutouts, the loads become much larger, and therefore you will see much larger cross-sectional areas over here. So these are the transverse stiffeners, say very similar to that, but in terms of functionality, but look very different from a shape point of view. Because if you're looking at these small holes as cutouts here, the cutout in this case is almost the entire fuselage cross section, because you want movement possible within the fuselage for various purposes, depending upon the type of aircraft, and that makes the design very different. So in addition to these, at the front end and the latter end, you will have much larger massive transverse stiffeners, which are called as bulkheads. So typically pressure bulkheads to take care of the internal pressurization that is there in most passenger aircraft which fly at a large altitude. So let's look at some nomenclature which I have already mentioned in passing in the fuselage. These are called as either frames or rings because of the shape that they have. It's a ring-like shape. That's why. If they cover all or most of the cross-sectional area, as I said, very common in the front and the back, but for larger aircraft, maybe you'd have something in between as well, but very long aircraft. So then if they cover most of the cross-sectional area of the fuselage, they are referred to as bulkheads or pressure bulkheads. And in the case of the wings and tail, as we see in this case, all these are called as ribs, very similar to the ribs in the rib cage of most vertebrates. So now let's look at some examples of that in more aircraft, so that we can see, depending upon the class of aircraft, how we make a decision on some of these things. For example, if you look at British Aerospace, and here we will take a look at not just the transverse members, which we were focusing on in the last couple of slides, but now we will focus some more on all of these structural components in a semi-monocoque kind of a construction. So here is an example of a high cruise altitude passenger aircraft. Okay, so once you know it's a passenger aircraft and it is flying at higher altitude and fairly large speed, you know that there has to be internal pressurization. This is a must, is a requirement from FAA and all the other certifying agencies in other countries as well, that you need to maintain a certain level of internal pressure. Otherwise, the pressure at very high altitudes goes so low that it's very difficult for most human beings to survive healthily for over a period of time. So you need internal pressurization, which means that these are like pressure vessels, which means that whenever you have a pressure vessel design, either a spherical design if feasible, or a circular cylindrical design, or at least an elliptical or oval design is what would be most efficient in terms of distributing the stresses, and therefore most fuselage cross sections, and in this case particularly if you actually see the contour, very close to circles. So all of these, this is taken from one end of the fuselage. You see that you are having all these circles looking as if they're becoming smaller, but actually they're pretty much the same size, but because of the way the picture is taken, it looks like that. But essentially each of them is circular in cross section, which means that it's going to reduce the stress primarily coming from the internal pressurization. So this is a British aerospace aircraft 146. Similarly, if you look at an Airbus aircraft over here, I don't have data on which aircraft it is, but similar to most older Airbus aircraft, where each one of these components that you see over here are the transverse ribs, which are placed along the wing of the aircraft in order to take concentrated loads which are coming over there because of an engine attachment and or where the spar ends, for example, because the loads reduce beyond that. So places like that, and also some of them purely as formers, and some which are purely as formers will typically have even larger cutouts. One could be because of the what needs to pass through that, but another could be because the structural loads are so low at certain locations closer especially to the wing tips, that you do not need so much of an area. It's more to maintain the overall airfoil cross-sectional shape that these are placed along the span. So this is the wing or the tail. You place them at different locations. They keep obviously becoming smaller and smaller as they go towards the tip with larger cutouts. So this is one class of aircraft, high cruise altitude passenger aircraft. Keep that in mind as we go on to another class over here. This is from de Havilland. This is a Canadian aircraft. Here you're talking of, compared to the previous one, the British aerospace vehicle that we talked about, this is smaller. So this is smaller and also a lighter, but it's also a passenger aircraft. But you see much simpler kind of a configuration because of the fact that once it is smaller, it's going to have much lesser loads, and therefore the requirements from a structural point of view also start coming down. It's a lighter passenger aircraft and it has a very simple configuration. If you look at in terms of the number of spars, you would see that there's just one spar here and another spar over here. There's just two spars are more than sufficient, whereas very large aircraft, some of the examples that you showed like Boeing 787 etc., you will have many number of spars in the wing because the bending moments are so large that a single spar may not be able to handle that. You need to distribute that amongst multiple spars. So two spar configuration for this small aircraft. Once again you have ribs. You can see these ribs over here. So similarly along the length, quite a few ribs over there, and then you have stringers and skin. So you see the stringers which are running along the length. So those are the stringers, and then of course the skin from this side it is taken off, whereas here on this side you can see it's still over there. So this is to reveal the skeletal structure that typical these kind of cutouts are given. So recollect the functions which we discussed in the previous class in terms of what the skin does, what do the stringers do, what do the spars do, what do the transverse ribs do, etc. Those functionalities remain pretty much the same irrespective of the class of the aircraft, just that the relative loads are larger or smaller depending on the type, and therefore the numbers that you choose, the pitch, which means the placement distance between adjacent ribs, etc. Those are going to be things that we as structural designers can play around with in order to optimize and reduce the structural weight to the extent feasible. Now this is flying at a fairly low altitude. It cruises at a fairly low altitude, which means that the certifying agencies will not require you to internally pressurize this particular aircraft, which means that it is not like a pressure vessel, which means that you can do with, like what you see over here, rectangular cross section of the fuselage. The airfoil, of course, for the wing, but for the fuselage, unlike the previous one which we saw almost was circular, because wherever internal pressurization is there, kind of a smooth surface like circular or elliptic or oval will be best to dissipate the stresses. Whereas here it's almost like, of course the corners are rounded, but essentially it's more like a rectangular, so that the height is similar when I go to the edge of the fuselage or this edge of the fuselage or in the middle. Whereas in a circular fuselage, you know that the height will be much more at the center of the fuselage at the tail, and it will keep reducing as you go closer to the windows, right? So that is essentially what is not necessary in this case, and you can actually take care of other requirements, non-structural requirements, to like maximizing the space for the passengers or whatever the aircraft is being put to use to. So that's the Twin Otter for you. Then let's go to another example, which is the Harrier, a military aircraft. So this is again a cutaway for that from Pilot Press. These are typical sources where you get these kinds of cutouts, like the Flight International magazine that I also mentioned. So now coming to this, what is the class of the aircraft? It is a vertical takeoff and sometimes short takeoff landing aircraft as well, which means that during the takeoff phase and landing phase, the loads will be very, very large on this, apart from the fact that it's a military aircraft, and the maneuvers can also result in very large G loads, which is stretching your flight envelope that we drew in an earlier class, the VN diagram. So you try, it goes much more than the previous two examples that we saw, which were typically passenger aircraft. So the N max that you have and the N min would be much lesser in absolute numbers for those compared to here. So which means that you will see there are numerous spars. In the previous example we saw just 2 spars. Now you see 1, 2, 3, 4, 5, 6, at least from what we can see in this cutout, you see almost 6 or more spars, which means that it is having much more load, bending load, and to be able to handle that, a single spar would be too massive and probably not accommodatable inside. So you are trying to distribute that load through multiple spars. So numerous spars. Similarly, you see there are quite a few ribs as well, but you see the ribs are not as close and as many as in the previous example, because in the previous example you had a passenger aircraft which was having a much larger aspect ratio, which means that the span is much longer compared to the other dimensions, which means that you needed more transverse stiffeners over there. Here it's typically most military aircraft will have a delta wing or highly swept wing like you see over here, in which case the aspect ratios will be very small, and because of that you do not need as many ribs, and the placement or the pitch of the ribs is also much larger. You see the distance between it, 2 adjacent ribs is fairly large. So that's the next thing. Then also you look at in terms of the skin configuration, the type of materials that are chosen, and also the thickness that is there. You'll have a huge difference between this and that because of the larger loads occurring in this particular case. So, but despite all of these complexities and different overall functionalities of the aircraft, the functionality of the components remains the same. So that is what is very key point for us to understand, and therefore all these terminologies that we learnt in terms of the semi-monocoque construction, primarily having a skin and all the skeletal structural components, each one of them, what they do is mostly the same across the spectrum of or different types of aircraft, right? Then you observe the rib geometries change from the root to the tip So if you look at the shape of the rib, it's going to be very, very different as you go from the root to the tip. One, of course, it's going to be much more massive here because you're going to have much larger loads as you go to the closer to this, and also where these armaments are there, like wherever you see these weapons systems from which the missiles, etc., would be launched, or even where the landing gear is attached, etc. There you see much thicker cross-section stiffeners, because if you didn't have them, or if you had much thinner ones, the load on the skin will be so large that the skin would immediately fail. Material failure would be there. Even though the overall load distribution might be good, the concentrated loads where these attachments of armaments and or landing gear or even engines are there. In this case, of course, the engine is integrated into the fuselage, so you do not have much of an issue there. From the thrust vectoring point of view, you need to take care of the different directions of loads, because the engine nozzle can change the direction, and depending on that you would have the different direction of thrust, which is how this aircraft is able to, without much of a runway, it's able to take off and land on a fairly short distance, or even entirely vertically, which is why it's called the stall. It's an attack aircraft. So you see from the root to tip, and as you go to the tip, if you look at many of these ribs at the tip, they are hardly capable of taking any structural load, but you still need them, because even though their load may not be large, you do not want the shape to change or size to change too much over there through very large deflections because of non-design loads, and therefore you want to keep them, which is why they are called as formers. So of course the English word former is also used to refer to past or something which has existed before, but it's not used in that context here. It's used from the word form, to keep that form. It is maintaining that form or shape or size, which is why it's called a former. Okay. So now, now that we have seen a range of examples, starting from large passenger aircraft to small passenger aircraft to military aircraft, and functionalities remaining the same, but there are subtle differences in terms of how they are utilized. Overall, if you look at the history, and I've purposely broken that as a high story, because it's a high story in the sense that how much of achievement has happened over a period of time. They say there are certain things in the aerospace industry which have been like landmark changes in terms of the way we design and utilize aircraft. One of them, of course, was the jet engine, the arrival of the jet engine compared to the earlier piston props and things like that, reciprocating engines. But another one is the composites, and the way they have made a huge impact. But overall, if you look at from the past to now, in terms of how the kind of loads that have changed, and also the amount of material we are allowed to use as part of the aircraft. So typically, the allocation is made by the aircraft designers in terms of what percentage can be used as a payload, what percentage of the maximum takeoff weight can be used as a fuel, what percentage is used as, let's say, the control surfaces, etc., and what percentage can we as structural engineers use to put materials to take the stresses and strains. Right now, that percentage in terms of what percentage of the overall aircraft's weight a structural engineer can utilize has come down drastically over the years. How much of weight was allowed for us earlier to how much of weight percentage is allowed for us now is a huge difference. So about 10% we have come down by. But at the same time, the loads that we are asked to take with that lesser amount of material is much more, which means that we have had to come up with more and more capable materials, and more than coming up with capable materials, it's ingenious placement of these materials in appropriate directions, especially in terms of the fiber orientations, etc., so that we can have an optimal overall structural design. So that's what we are doing. We are carrying more with less amount of material. So that is essentially been the story of structural requirements over almost a century. So In fact, it's quite shocking to, if you look at an average of wing loadings, by which we mean, of course, as most of you know, is the overall weight of the aircraft, the gross takeoff weight, which is going to be equal to the lift during cruise. So that weight of the aircraft divided by the area of the platform area of the wing. So W by S is what you call as the wing loading. Okay. Now that wing loading has gone up by as much as 13 times. So whatever it was the requirement in terms of Newton per meter squared about 100 years back, now it is 1300 times. So that is as a percentage is what you're looking at. And as I said, we are expected to do all of that extra work by using much less material. So the weight fraction that is allowed for the structural engineer, what is called as the structural weight fraction, that is the total weight of the structural elements, all of your skin, stringers, ribs, the spars in the fuselage, the wings, the tails, all of them put together, divided by the weight of all of them put together, divided by the weight of the aircraft as a whole, is used to be given a luxurious 40%, or at the most, the most stringent, best designs at that time would used to be about 30% structural weight in the about 100 years back. But now we are expected to do the same, actually much more work by having much lesser percentage for the weight, because we want to give as much as possible for payload, to be able to take more people, or to take more cargo, or to take more weapons in a military aircraft, or we want to fly them for a much longer distance, longer haul flights, or we want to take more fuel, which means again longer haul flights or better performance, things like that, because of which the weight percentages have been moved away from structures to other areas, and therefore typically less than a quarter of the weight of an aircraft today is typically, and this is again data I have is of 2016, that's about 7 years back. I wouldn't be surprised if this has come down to 20% for some of the latest aircraft designs. So almost 1/4 to 1/5 is what we are trying to have for the structure, and still we are able to handle 13 times the weight is what we are looking at in terms of, compared to the same platform area wing earlier days, for the same platform area wing design today, you should be able to take an aircraft which is 13 times heavier. So that's a huge remarkable improvement that has been made in terms of material choices and geometry choices, and which really needs to be appreciated. Many times a lot of praise is given to a lot of other areas, but this is kind of overlooked. But this data will show you how important the structural engineers and materials engineers contributions have been. In fact, it wouldn't be an overstatement to call it an evolution that has happened in both material and structural design. So just to put it in a graphical terms, what we are talking about there is that the weight, that is the gross takeoff weight divided by the area, the platform area of the wing, in Newton per meter squared, the SI units that are typically used in 1917, which is about 106 years back, was about 350 Newton per meter squared. But now you see it is as high as 4,800, and it's not, again, now as I said, it's 2016 data. So this is just over a century. We are trying to go from 1917 to 2016 in terms of the years. And we have gone up from 350 Newton per meter squared to about 4,800 Newton per meter squared. So that is the kind of wing loadings we are dealing with now. But the structural weight percentage, as I said, has come down from 35% of average to about 22% average, which is a drop of about 13%, which is a huge drop indeed. So in terms of percentage of that, if you're looking at it's much more in terms of almost like 50% improvement that we have had. So then let's go to a little more detailed classification in terms of the load-based components. We have had a load-based classification of the different aircraft, but now for a given aircraft, what are the components? And we already said they have to be beam and or shell-like structures, right? Now, beam-like structures, we talk in a more generalized term, is essentially one-dimensional structures. In other words, the cross-sectional dimensions very small compared to the length. The other case, we're talking of thickness very small compared to the length and the width, which is a plate or a shell-like structure. And we have seen examples of both, starting from the skin, the spar webs, both of which are plate-like structures or shell-like structures. On the other hand, all these stringers, etc., the spars are all like beam-like structures. And then, of course, you have these box beams that we talked about, formed by the skin along with these spar webs, essentially hollow, closed cross-section beams. So, first example is this is rare in the case of most fixed wing aircraft. Yes, if you take individual stringers, yes, many of these are either bars or columns, depending upon whether they are on the top or the bottom. For example, this is the fuselage, think of it. So it's the biggest load here is the self weight, which means that it is bending downwards at the tip, at the nose and the tail of the wing. So essentially the top stringers are mostly under tension. The bottom stringers are mostly under compression, which means that these are almost like rods and these are like columns. So that's essentially what we are talking of. But even more so in the case of helicopter rotor blade flex beams, where the centrifugal forces are so large that the bar is a very, very classical example over there in the primary lifting surface itself. But in the case of the fixed wing, it's more in terms of the stringers and also the spar caps, the top and the bottom, some of which are under tension, some of which are under compression. If they are under tension, they are called bars. If they are under compression, they are called columns. Together, if they are going to at sometimes take tension, sometimes compression, therefore you call them as bar columns. Next, again a one-dimensional structure are the loads that they take. Instead of axial force, we now have the torque as the dominant load, and then you typically call such long structures as shafts. Once again, because they are long, which means long and slender, cross-section is small compared to cross-sectional dimension is small compared to the length, and therefore again a 1D structure. The next example of a 1D structure, very common again, is the spar, where you have a bending moment as the main load that is coming, and there you typically call the same component as a beam. So in other words, all of these, whether it's a bar, whether it's a column, whether it's a shaft or it's a beam, they are essentially one-dimensional structures. From a modeling point of view, it will be most appropriate for us to model it as one dimension, so that the computational requirements are very less, both for analysis and design, or structural health monitoring, or iteration in optimizations, etc. All of these cases, you will see that you are going to have much better ability to design optimally if you model it as 1D, as long as your dimensional reduction is good enough. Next, you're going to a different kind. Instead of 1D, now we have a 2D kind of structure, and this is typically used with shear force, which is essentially coming from, let's say, the torque or the transverse loads, because the lift and the drag, though the main effect of them is to cause bending, the secondary effect of them is to cause the shear because of the transverse loading, and therefore both due to torsion as well as due to shear, due to transverse forces, you can have these kinds of members playing a very important role, because these panels, they can easily take that kind of a load, unlike any of the above. But of course the shaft is an exception, where it's also talking of a torque over there. So that comes under the category of something which can be modeled both as 1D and 2D, examples of which we saw in a couple of classes earlier, where I just plotted a cylinder to show if it's a very long cylinder, you can model it primarily as a 1D, but if it's a short stubby cylinder, you can model it more as a 2D to be more accurate. So which means that there are certain configurations which can be modeled both as 1D and 2D. So we'll have to take a call based on the length to diameter ratios for such entities. But essentially shear forces are mostly taken by 2D panels. Some of these are flat, some of these have a curvature, but most of them have, because of the large size over which the curvature takes place, each individual panel may not have such a large curvature, except at the nose, for example, of the fuselage, or the leading edge of lifting surface like the wing or the tail. There the curvatures are large, but otherwise most other areas you can treat for most practical purposes as a flat panel, right, in spite of the small curvatures, initial curvatures that exist. So these are the 4 important types that you need to keep in mind: bar columns, shafts, beams and panels. Sometimes you can divide the bar and column to 2 separate ones also, bars and columns, depending upon whether it's dominant tensile load or dominant compressive load. But most of these will be able to handle both to some extent, though primarily it will be designed for one. So the next is the need to model an actual 3D structure, because as I said, in reality everything is 3D, just that it offers us the opportunity to model it in a dimensionally reduced manner, so that we'll have more computational efficiency, which is what our goal will be in the rest of this course. Which means that dimensional reduction is necessary. This is not something new. This has been done not only in aerospace but also in other fields like civil engineering, where people have had these beams and columns and the floor panels, etc. So people have been dealing with these kinds of loads for static structures and for automobiles and many other moving structures as well, even ships for that matter, many of which have existed, of course, way before aircrafts came into being. Which means that a lot of the knowledge has helped us to have a jump start in terms of how we design aircraft structures. But nonetheless, the kind of dimensional reductions that they used to do to go to a beam theory or to go to a plate or shell theory, we are doing much better now, because whenever you go from something which is reality to a mathematical model, obviously there are some assumptions involved, which means that there is going to be a reduction in the accuracy. But how much of accuracy is reduced? Is it a 10% reduction in accuracy, or is it just a 1% or 0.1% reduction in accuracy? In which case, in the latter case, you would be happy to go ahead and do that, right? So that is what is important, and that depends upon how you carry out this process. So that's where it's very important for us to be process oriented rather than goal oriented. The goal is always very clear. We want to model the 3D as 1D. But how do you go from here to here? There are many textbook formula that are there, which are very simple and easy to apply, but the drop in accuracy will be something that you can't live with in a design, especially detailed design, etc. So you have to do this dimensional reduction appropriately. In other words, there's a lot of work from a theoretical point of view going from this to this, but once it is done for once, then you can start using it on a routine basis very fast, so that in other words, the efficiency improves drastically. But you should have confidence that you have done this derivation well. And this is not something that we will do in this course. This is something that we will take as it is, because others have already done it and fairly well established, validated, and it is verified along with experimental work as well as flight tests, etc. So they are well validated theories. So we will just use that theories. But I'm saying that those theoreticians who derived those really spent a lot of effort in terms of going from here to here. But now that they have done that, we can start utilizing that for all those structures that are there, and those are the only structures that are typically there in all aircraft, or in fact all flying vehicles, and therefore they've made our life much simpler. But to do that, they have struggled quite a bit, and there's a huge history behind that. So dimensional reduction for the first 3 cases, 1D generalized beam theories, even though they are shafts and bar columns in that, we call all of them together as generalized beams. So though the classical term beam is referred only to dominant bending loads, even when there are torques and axial forces, tensile or compressive, we tend to call all of them together, as club them as a single family of one-dimensional structures and call them as beams. Similarly, when you club all of these panels, you typically call them as generalized shells. Some could be large in one direction, small in the other direction, or they could be of the same order of magnitude in both the length and the width, etc. Some could be typically very thin structures. Some could be medium thickness, still the thickness is small compared to the length and the width. There are certain subtle complications in each one of them. Neither of them is completely simpler compared to the other. Certain of them have certain kinds of complication, the other has different kinds of complications. So we will look at some of those examples as we go forward. But as I said, because we are going from the reality to the model and we are reducing the number of dimensions by 2 in this case, from 3 minus 1, that is 2, and from 3 to 2, that is 3 minus 2, by 1 dimension we are reducing. In this case we are reducing by the thickness dimension. In this case we are reducing the cross-sectional area to a point. Here we are reducing the thickness to a point. So it's only 1 dimension which is being reduced from going from 3D to 2D. Whereas going from 3D to 1D, you're 3 minus 1, you're getting to 1D, therefore you're reducing a cross-sectional area to a point. And each cross-sectional area is reduced to a point. The loci of all of those points become what is known as the reference curve or the reference line of a beam, right? So because you're doing that reduction, the efficiency is going to go up a lot, because 1 dimension reduction itself will give you about 10 times improvement in the CPU times. In other words, if you are spending, let's say, 100 seconds on a particular problem, it will come down to 10 seconds, 100 by 10. On the other hand, if you have been able to reduce that from 3D to 1D, it might go by 10 power 2, which means that where you are spending 100 seconds, you spend only 1 second. So what is more important is not that difference 99 seconds, but 99 seconds into hundreds of thousands of runs that you're going to have for the same problem, which is going to be, in terms of the human resources and time, humongous amount of savings. So, but always remember that in doing this process, you are moving away from reality and therefore accuracy is dropping. But the modern methodologies are such that the drop in accuracy is as low as 0.1% or so. For all practical purposes, if you plot results from this, like stresses or strains or displacements, deformations, rotations, all of them will be, for the naked eye, it will look one on top of each other. So that is the level of accuracy that we have achieved by appropriate dimensional reduction. So this is not something that we need to be worried about, unless somebody is still using some old textbook like formula where yes, the accuracy drops will be very large, and then they might conclude that this is not a good idea. But if you are using the current state of the art in terms of how you do this dimensional reduction, then this is something not to be concerned about at all, but this is a huge advantage to have. Are there any doubts until now? So we'll move on to a different thing now. Yeah. So the next thing that we'll be looking at is, so far in the last class and this class, first part, we have been looking at the geometry, because both whether it's the beam or the shell, essentially it's a geometric classification that some things, one dimension is very small or one dimension was very large compared to the other 2 dimensions. But now we come back to material. So as I said, these are 2 choices, material and geometry, that we have to keep making, and many times it's iterative. You choose a material, you make a certain geometry choice. Again, because of that geometry choice, you might have to tweak that material a bit, especially in terms of the placement of the fibers, which direction you put, etc. So which is also a material decision. So then again you go back and look at any changes to the geometry. So kind of you need to be jumping from one to the other, but these are 2, you can almost think like juggling. You're juggling 2 balls at the same time. So you're essentially looking at playing with the material choices and the geometric choices, and within the geometry again sizing and shaping, number of components, the placement of components, like we were talking about the pitch of the transverse ribs, etc. All those decisions need to be made, and this is something which most other people who teach this particular course at Georgia Tech, 3140, they use a textbook. We are not using a textbook for this course, but they use a textbook by Bauschow and Craig. And Bauschow and Craig has a very good explanation of this, and most of the material is taken not from the book, but I was a student of Bauschow as well, so I happen to have his class notes, and most of this is taken out of that. So there are three main ways in which a structural design is done, and very easy to remember. All of them are starting with S. One is a strength-based design, the other is a stiffness-based design, third is a stability-based design. Now, it's not that one is more important than the other or whatever. It's just that for a particular component, one might be more dominant than the other. But usually you will consider all three, if not all three, at least these two. Because what the strength-based design tells you is that you ensure that failure doesn't happen. Okay, or at least if failure happens, it happens so late or in such a drastic condition and emergency situation that is rarely experienced in the actual flight of any flight vehicle. Then what this does, on the other hand, is that in spite of ensuring that material is not going to fail, it is possible that the deflections are very large and maybe unreasonable and too much to handle. So a stiffness-based design will ensure that there is some flexibility, but it is not so flexible that it can cause issues as far as the very running of the vehicle is concerned. So that is what this does. And this is, of course, in terms of ensuring what is here ensured is material failure is avoided. Here geometric failure is avoided. So you try to avoid geometric failures like buckling, etc. And the extended version is what we discussed earlier also in terms of aeroelastic instabilities like airfoil divergence, and you have the flutter and things like that. So those can be avoided as well. But here we'll purely see from the buckling point of view, from a stiffness point of view, and from a strength point of view. And when we're doing this on the lines of Bauschow, I will take this opportunity to not only introduce these three design paradigms, but also introduce different kinds of structural elements when talking about each, instead of talking about the same structural element and talking about this and that for the same element. Because our time is limited in terms of the course, we want to see that we can explore the different types of component geometries that are there at the same time while talking about how this has an implication on the material selection. So we will take up three different kinds of configurations. So let's go ahead and start with the first one. Before that, we will make certain general remarks in terms of the material selection. So many of which you would have already looked at in one of your previous courses. Was more like a summary directly relevant to what we are going to discuss in terms of the strength, stiffness, and stability based designs. So the material selection, as you know, is a very, very important part of the structural design. And the physical properties, if you take of three commonly used alloys, metallic alloys that are employed in the aerospace industry, were employed in much larger fractions, weight fractions earlier, but slowly they are reducing, but still have a huge role in most aircraft. And those are aluminum alloys, titanium alloys, and iron-based or steel alloys, right? Now, examples of how they look under various configurations are shown on the top. There's an example of an aluminum alloy, example of a titanium alloy, example of a steel alloy. And when you have these, one of the things that we will be considering when we look at the strength-based design is, apart from yield stresses, we'll also be looking at the ultimate tensile strength. Of course, where compression is the dominant load, you have to look at the ultimate strength in compression, but here let's look at the ultimate tensile strength. Again, in each one of these, whether it is the steel or the titanium or the aluminum alloys, there are a very large number of alloys, and there's a huge range within each alloy. There again, depending upon certain subtleties in terms of the manufacturing processes, etc., there can be quite a lot of variation, which is taking ballpark values in terms of relative orders of magnitude. That's what is important. So don't hold me by these numbers. There can be a fairly wide range. So now if you're looking at the strengths, typically it's given in megapascals, and you have 620 for aluminum, 1900 for titanium, and about 4100 for steel. So purely if I'm making a decision based on the ultimate tensile strength, I very clearly see that this is a winner by a big margin. I would rather use steel for everything, but that's not the way we go, right? So there must be other considerations, and which is what we will try to look at. Next, if you are looking at a stiffness based design, Then the aluminum alloys have about 70 as gigapascals as their stiffness. So you see a huge difference in terms of the what we saw for the ultimate tensile strength in megapascals and the Young's modulus moduli in terms of gigapascals, about 1000 times, and that is very easy to see because E represents the slope between them, and at least until the linear limit you would see that typically the strains are fairly small, so the stress to strain is fairly small, and therefore you have Young's modulus, Young's moduli are typically much larger for the same material compared to the strengths. Now this is about 70. For titanium alloys it's of the order of 115. Once again steel is a winner by a fairly big margin, about 210 gigapascals Young's moduli. So it's very clear that if you compare with aluminum and titanium alloys, the ultimate tensile strength of steel is much larger, right? Similarly, if you look at from a stiffness based design, you can see once again that the Young's modulus of steel typically is much larger compared to those of aluminum alloys and titanium alloys. Now, whether it is a strength based design or a stiffness based design, if it's purely in terms of these absolute numbers, it's very easy to make the decision and say that steel is the best choice. But we know that's not the reality. Most aircraft have very less amount of steel, especially in landing gears, that is the undercarriage, etc. It's not so widely used. So obviously there are reasons for that, and you're pretty much aware of that. So that's why I'm kind of rushing through this. So steel is the strongest and the stiffest, but we know that it's not preferred always, and the primary reason is the weight, as most people would say, that is much heavier, which means that more from a more engineering perspective, material property point of view, we are talking of the density, the mass density in particular of these three materials, and we are looking at. But is that a right answer is what we want to explore in this. So the materials again, of course there are many other materials which are used in aerospace vehicles. We are just focusing on three just for a comparative study over here, and these are kind of dominant materials, have been for a long period of time before composites took over to a larger extent. So the next thing we are looking at is in terms of the mass densities. Again in SI units, kilogram per meter cube, we typically see aluminum alloys have 2700 kilogram per meter cube, whereas the titanium alloys, again there's a wide range, I'm just giving you ballpark values, 4700 kilogram per meter cube, and steel, you see here it fails in terms of the utility for weight critical applications like aerospace, where even a small weight penalty would be a huge payoff in terms of the performance. The performance is going to go for a toss, and therefore this is going to be something that is what was a deal clincher for it earlier in terms of E and sigma U now becomes a deal clincher more in terms of these. But then we can't compare these two properties separately. There has to be a way of combining that, and that's where we come to the definition of what we call as the specific properties. Okay, so steel is not always the preferred material between these three compared to aluminum and titanium alloys, because it's far heavier, the density is much larger. But is this really the case is what we are trying to explore over here. In weight sensitive design, there has to be a compromise typically between conflicting characteristics, and this is very common in design. You're always going to have to make decisions between two things or more than two things which are all going to be conflicting with each other. Any decision you take on one is going to impact on the other, etc. So, but here we are talking of a weight sensitive design. We want a reasonable amount of strength, we want a reasonable amount of stiffness, but yet we want a light structure. So that is essentially what we are taking. So which means that we need to compare material performance for specific structural applications. So we have to go case by case and see which material suits it best, and which is why you see even on modern aircraft, some of the latest designs also, you'll see it's not made out of a single material. You will see different components made out of different materials, and they're all coming together in some sense through joints and various other things like adhesives and or rivets or bolts or various kinds of integral manufacturing as well. So all of that happens, but it has to be done on a case by case basis is what we are saying. So what are we trying to do over here? There are three primary categories, as we already saw, of design situation: one based on strength, one based on stiffness, other based on stability. So I'm not sure if we'll cover all three today, but we will take it forward in the next class as well. But essentially, for each one of them, we need to get certain material performance indices. So these material performance indices need to be derived for keeping in mind that it is a weight critical design. At the same time, what is the dominant need of that performance index? In one case, you do not want it to fail. In one case, you do not want it to deflect beyond a certain level. In other case, you do not want a geometric failure. So taking care of those and at the same time ensuring our weight sensitivity requirements is what these performance indices will do. Two of which I think you will be familiar with, but the third one is something that is usually not taught in most courses, but Bauschow does and I will do too. That is the stability based performance. So we'll start with the strength based design. So as I said, the material failure is the criteria here. The secondary criteria is that you want it to be weight critical as well. As I said, in each one of these we will introduce a different kind of a structural component so that we have two utilities of the same exercise. One is we are learning about strength based design, at the same time we are learning about a particular kind of component that is used in typical aircraft or any flying vehicle. So you take a structure like this which is having a length L, which is having a breadth B, and which is having a thickness H or a height H that is shown over here. Now we introduce a reference frame going along with this. So along the length we introduce the coordinate x1 and the tangential vector b1, small b, lowercase b1, and similarly along the width we will have x2 and b2, and we will have along the thickness x3 and b3. You will see that b2 and b3 are shown to be functions of x1. In other words, this is having a pre-twist. In other words, it is even before the application of any torque or any other load, when it is free, it is having between this edge and this edge, they are not parallel to each other, they are kind of twisted already, because that's the kind of configuration we want for a particular application. And very classical example of this is a helicopter flex beam, where you will typically have this. It's also possible to understand the reason, because it's very similar to your fixed wing having a wash in or a wash out. So similar kind of reason is over there, and also in terms of trying to get an extension twist coupling, because the extension loads in a helicopter are very large because of the centrifugal forces, and control is always done by the twist, as we discussed in a previous class. So these two being coupled, the coupling can be made more beneficial by introducing such a pre-twist. Okay, so let's keep this in mind. But usually these pre-twists are fairly small, and because they're spread over a very large length, which means that you're not going to have too much of an issue dealing with that. That's fine. We'll keep that. That's besides the point. Next, we will focus on the strength-based design. So we'll make certain simplifications, because our only goal here is to get a material performance index. So we will make certain simplifying assumptions, some of which may not be valid and some of which we may not make in the rest of the course, but this is good enough to get to that material performance index. All I want to do is, I have a set of materials, candidate materials for a particular component. Which one will I choose? What particular properties or combination of properties will I compare? So that's what we are trying to get at. So the criterion, as I said, is material failure, as opposed to stability based criterion, where we will talk about failure but a geometric failure there. Now it's material failure. So consider this particular sheet. It could be a metal sheet, it could be a laminate made out of a composite, but essentially it's of this shape, such that your L and B are very large compared to H, and it's also possible that your L is large compared to B if it's a helicopter flex beam, for example. If it's a panel of, let's say, wash in or wash out wing, fixed wing, then L and B may be of the same order of magnitude, but in a helicopter rotor blade, L will be much larger compared to B. That doesn't matter, it's besides the point, but I'm trying to give you additional information to show you the relevance to actual aerospace decision making. So now consider this particular sheet, it could be a metal sheet or a composite laminate under tension. So the only load that we are applying is a pull load on either edge of this, or you fix one edge and pull the other, but each is equivalent of the other. So, but essentially we are trying to extend this, that is the primary effect. Now, when this happens, there is going to be we'll assume a Saint Venant's principle. Saint Venant's principle, all that it says is that close to where you are applying the load or applying a boundary condition, there the actual way in which you apply the load and the actual way in which you implement a boundary condition is going to affect. But once you go to the interiors of the structure by an order of magnitude equal to the cross-sectional dimensions, then in that interior, it doesn't matter exactly how you are applying that axial load, because the axial load can be applied as just one single force or F, or I can apply F by 2, F by 2 over here, or I can apply 3 forces F by 3, F by 3, or a uniformly distributed force F by A pressure, or let's say stress, F by A stress, that is applied on this cross-sectional area of A, so that F by A into A becomes F. So that I can apply in any of these ways, but the resultant force is always F. So whereas close to this boundary, it will matter how I apply that load, but in the interior portion in which I am interested in right now, it doesn't matter how you apply the load, it's the resultant of that load which is of significance. This is called as Saint Venant's principle. Saint Venant's principle is very, very critical and useful for a lot of other applications. We will revisit that probably in the future. But for now, I'm just stating that in passing, because that's not our main goal on this slide. So because of that, you can say that in the interiors, irrespective of how I fix this end and how I apply a force at this end, the end result is that there's going to be a uniform stress distribution at the interior cross section. Now, the total load carrying capacity of this, sorry for the fonts, I think I changed from my Mac to the iPad, so some of the fonts have got for a toss. I tried to change most of them, but some of them I haven't changed. So the total load carrying capacity in this case would be, in other words, I'm fixing one end, I'm trying to pull this end with a force P, and I'm going on increasing the value of that load P, a tensile load, until this material fails somewhere in between, right? So when this happens, you can see that the uniform stress is sigma, and the cross-sectional area is the breadth times the height of the cross-section, which is B into H, okay? Now it's very clear that if I keep on increasing P, it will fail when sigma reaches sigma u. Of course, there are subtleties in terms of, first it will reach a linear limit, and which is called as the proportional limit. It could reach a yield point, and stress strain curve itself looks very different for those three alloys, etc. Let's keep all of that besides the point right now. Let's focus just on deriving the material performance index for failure at this point in time. So the maximum load at which maximum load that this particular structure can take in this configuration is the ultimate tensile strength times the cross-sectional area. It's also possible that there is necking, what we call as B and H, reducing in size as we get into the plastic regime, etc. So all those complications we are leaving out. As I said, many assumptions are involved in this whole process, but still this works, and works brilliantly, which is why it is important to get to the result. So the total structural mass of this, because it's not only that I do not want failure to happen or want to delay the failure to the extent possible, but also I want, it's a weight critical design, it's an aerospace application, so I want to keep the mass as low as possible. So what is the total structural mass. Very easy to see. If you can kind of ignore the pre-twist which is there, which is fairly small, this is more like a cuboid. So the volume of the cuboid is length into breadth into height, LBH, multiplied by the density of that particular material, which we will call as rho. The things that I am highlighting in blue are essentially material properties. The ones which are not highlighted are the geometric features. Okay, so B, H, L are all geometric features, whereas sigma u and rho are the material properties over there, which are in blue background. So now we have two equations. One is for the maximum load that this can take, and the second is for the mass of this. And so now I can use these in order to get the P relationship by eliminating certain other things over which I have typically a choice. See, usually I do not have a choice over many of these quantities like L, etc., which is kind of dictated by the span of a wing or the length of a helicopter rotor blade, which are all typically aerodynamic decisions. So what I can decide on the other hand as a structural designer in terms of geometric features are like H, or I can decide sometimes B also, because the breadth in terms of number of panels, I can have more number of panels of smaller B. So things like that I can decide, but L typically I will not have much of a decision. Similarly, the mass is something which is allocated, as we saw, 20 to 22% or 22 to 25% is what we are allocated for the structural components, of which we would have allocated a smaller percentage for this particular component, because it's for all components put together. So you would have not too much of a say over that. If you can reduce it beyond that, well and good, but we have an upper limit on that. So these are not some things that we can play around with too much, but these are going to change depending upon the change of the material properties. So instead of looking at sigma u separately and comparing for different materials, instead of comparing rho separately for different materials, if you compare the ratio of that, that is what is your performance index as far as strength is concerned, and that is what is critical in comparing steel, aluminium and titanium that we were trying to play around with and see which is better than the other. So for a given mass, that is M that we are talking about, and for a given overall geometry L, then you have to have a choice in terms of choosing a material which has the maximum sigma u by rho, so that the material performance index for the structure, for the strength based design is going to be maximized. So that is essentially what we are going to look at. So I think we'll probably close with this and go into the other two, that is the stiffness based design and the stability based design at the beginning of next class. So we'll not have any homework for today. But I would like you to come back with the repeat what we talked about in terms of the actual plots, like something like this. Thank you.